Hi everyone, and welcome back to Caroline's Chemistry. Today we're looking at significant figures and what they are, why they matter, and how to use them properly in your A-level chemistry exams. We'll cover how significant figures link to precision and uncertainty, how to round values correctly, and the one place students most often lose easy marks because of sig figs. And make sure you watch right to the very end because I'm going to go through the exact rules for when and how to use significant figures and when not to, so you know exactly what examiners are looking for. And if this is helpful, don't forget to hit like and subscribe now. Let's get started. Welcome. So let's mention first why significant figures matter in chemistry. And they matter more than, say, when you're doing maths, because chemistry is a practical subject. Most of the data that we generate uses pieces of equipment. So for instance, if I have a volume of 20 centimeters cubed that I'm using in a titration calculation, then I had to measure that 20 centimeters cubed with a pipette or another piece of apparatus. So those pieces of apparatus, they have apparatus uncertainty. So that's the amount of error associated with that measurement. And it means, therefore, that I can't give an answer like a concentration of a solution that's more precise than the apparatus that you use to get that answer. So say, for instance, your pipette has an apparatus uncertainty of plus or minus 0.1 centimeters cubed. Well, I can't then give my overall answer from a titration of that concentration being like 1.333333 requiring moles per decimeter cubed. Like, it cannot be that precise because the equipment was not that precise. Okay, so let's make sure we're super confident about what we're counting as significant figures and what we are not. So starting with the first number, if we were to take that to one significant figure, then we are rounding down from the 9.3, so that is 9. Two sig figures, then it's 9.37, so to get two sig figs, we round up to 9.4. 4 sig figs, we round up from the 7/8, so 7/8 rounds up to 8, so 9.38, 1, 2, 3 sig figs. 4 sig figs, then again we need to round up because it's 3, 7, 8, 6, so that 6 rounds up to a 9, so 9.379. And 5 significant figures, then the next number is a 5, so that also we have to round up. So it becomes 9.3787. That's 5 significant figures. Okay, next one. For 1 significant figures, then we take that first 4. And then we need 6 zeros. Have to write quite small there. The next significant figure is the one next door to that 4. So that's the 2. Next door to that is a 0, so we're just rounding down to 4, 2, 0, 0, 0, 0, 0. 3 significant figures, we now need to take into account the next door 0, which doesn't change anything. So that 3 significant figure is the same as the previous one. 4 significant figures, we now need to think about the next 4. So we have 4, 2, 0, 4. That 0 now counts as a significant figure because it's like trapped in the middle there. And then the rest are zeros. And then 5 significant figures, we have 4, 2, 0, 4, 3. There's our 5 sig figs. Again, that 0 counts because it's in the middle. And then the other 2 zeros that do not count. So any zeros that are on the end of a big number do not count as significant figures. Now the next one is a much smaller number. The 0 at the front now doesn't count, so 0 point does not count as a significant figure. So our first sig fig is just 9. The second sig fig is 0.90. So now because that 0 is after a number, it does count as a significant figure. 3 sig figs, first 0 doesn't count, 904, that 0 in the middle counts. 4 sig figs, 0.9035, rounding down from that next door 2. And then the 5 significant figures, 0.90352, again rounding down from the 1 that was next door. Okay, final one. So the zeros that we see initially, so the 0.00, they do not count as significant figures. Our first sig fig is that 2. The next one, 0.002, we then have 3 9ths, so we have to round it up to 4. Then we have 0.00239, because the number next door to that 9 is 4, so we round that down. Then we have 0.002395, because it was 48, so we have to round up to the 5. And then finally, 5 sig figs, 0.0023948, rounding down from that final 2 next door. So these rules of significant figures apply for the majority of chemistry calculations. Like most GCSE and A-level calculations in chemistry are using multiplication and division. So this means this is the general rule you're going to follow. Your final answer needs to be to the least number of significant figures that your data has. So what that means, for example, let's look at the first one. Calculate the average speed of a car that travels 1,557 meters. That is 4 significant figures in 95 seconds. That is 2 significant figures. To find the speed, I do the distance divided by the time, which gives me an answer of 16. Now, 16, 1/6, that's 2 significant figures. And I have to give my answer to 2 significant figures because the 95, that's the lowest number of sig figs. That's also 2 sig figs. The second one, however, the second example is 95.0. So we now have our data as 4 sig figs, the 1,557 meters, and 3 significant figures, the 95 seconds. So my answer is still 16, but it's not because 16 is 2 sig figs. My lowest number of sig figs is 3. So it's therefore 16.4 meters per second. So you can see there the difference between the two. Look for the piece of data that you are using that has the lowest number of sig figs and give your answer to that. Okay, now the second rule comes with a big caveat. You can only use it when using an addition and subtraction in your answers. An addition and subtraction only. If you then do another step to the calculation that involves a multiplication or a division, then you're using the rules that we just talked about. So if the calculation is only using an addition and subtraction, then this is the rule that we follow. You are now not worried about the number of significant figures at all. You are trying to preserve place value. And what that means is look at the number of decimal points that your answer is given to. So for the first example, the 263 and the 1282, those are all whole numbers. So your answer should be a whole number. In this case, 1,545 kilojoules. But if you look at the second one, we have 3 decimal places and 1, 2, 3, 4, 5 decimal places. So the 0.154 grams, 3 decimal places. The other number, 0.01234 grams, that one is the 5 decimal places. So to preserve place value there, then I need to preserve the least precise number. That is the 3 decimal places. So my answer there would be 0.166 grams, giving it to 3 decimal places. Now, the place where you most likely find this is in A-level when you get to things like Hess's law diagrams. That is the most common place where we might find them. Thanks for watching, and if this was helpful, don't forget to hit like and subscribe now so that I can help you do the very best you can do in your GCSE or your A-level chemistry.